viewers, welcome to CEC UGC online lectures. In my previous lecture, I had discussed the factors affecting SN2 mechanism. In today's lecture, we shall be discussing the effect of nucleophiles on SN2 reaction. In my previous lecture, I have already discussed the effect of substrate and the leaving group on the rate of SN2 reactions. Before we begin our discussion on the effect of nucleophile on the rate of SN2 reaction, let us first familiarize ourselves with the concept of basicity versus nucleophilicity. Any species which has lone pair of electrons on it or has a negative charge can act as a nucleophile or a base. So, when does a species act as a nucleophile or a base will depend on the nature of the substrate. That is, whether it is reacting with a proton or with any other electrophilic atom other than hydrogen. So we can say basicity is a subset of nucleophilicity. All nucleophiles are Lewis bases as they can donate a pair of electrons. We call a nucleophile a base when it forms a bond to a proton. So, two types of events can occur. First, what is basicity? Basicity is when a nucleophile attacks a hydrogen atom. Whereas, by nucleophilicity we mean that nucleophile is attacking any atom other than hydrogen, say electrophilic carbon atom. Now let us discuss this concept in detail. Basicity is a thermodynamic property. As we know, most acid-base reactions are reversible reactions. So they can be measured by an equilibrium constant that indicates the tendency of the base to abstract a proton from acid, as a result of which a new bond is formed between a base and a proton. So here I have shown that a base OH hydroxyl group is acting as a base and it reacts with water, resulting in the formation of another molecule of water and a conjugate base OH of acid 1. Now in this case, the position of the equilibrium depends on the relative stability of the species involved. That is, if the conjugate base of an acid is stable, then the reaction will be favored in the forward direction. Now if we talk of nucleophilicity, then nucleophilicity is a kinetic property because as we know, most nucleophilic reactions are not reversible. Since they are not reversible, we cannot measure them by equilibrium constant. That means we will have to measure the rate of this reaction by a rate constant. This will depend on how quickly a new bond is being formed between a nucleophile and an electrophilic carbon. As you can see on your screens, in this case, hydroxyl group is acting as a nucleophile and it attacks the electrophilic carbon through its non-bonding pair of electrons. In the process, it pushes out a bromide anion and an alcohol is formed. So what we find that the same species, which is OH minus, can act as a base when it reacts with a proton, whereas it is acting as a nucleophile when it reacts with an electrophilic carbon. I can take a simple analogy here. That is, if we talk of a girl and consider her relationship to her father as well as her brother, then girl is same, that is, I can say that it is a species which is having lone pair of electrons on it, but its behavior, her behavior with her father would be different from how she behaves with her brother. So, in a similar manner, a species will act as a nucleophile when it reacts with an atom, electrophilic atom other than hydrogen. Since the nucleophile attacks the substrate in the rate determining step of an SN2 mechanism, the rate at which substitution occurs varies from nucleophile to nucleophile. In other words, nucleophilic strength or nucleophilicity is a measure of how fast a nucleophile displaces leaving group from a suitable substrate. So now we have to look into what are the good characteristics of a nucleophile, or what is it that will make a certain species a good nucleophile. Let us look into the factors. The first factor is the magnitude of charge. When comparing species that have same nucleophilic atom, a negatively charged species is more reactive than a neutral one. In other words, a base is a better nucleophile than its conjugate acid. For example, if I consider an example of OH hydroxyl group, which is a conjugate base of water, then we find hydroxyl group is a better nucleophile because it has a negative charge on it, whereas water will act as a nucleophile through lone pair of electrons on its oxygen. So it is a weaker nucleophile, or the rate of reaction will be low. On similar basis, we can say that alkyl oxide ion, which is a stronger base as compared to its alcohol, which is its conjugate acid, so it is more nucleophilic. Similarly, carboxylate ion, which is a conjugate base of carboxylic acid, is also more nucleophilic than carboxylic acid. As long as the nucleophilic atom is the same, we have to remember the more basic the nucleophile, more reactive it is. Let me illustrate this by taking an example of an alkyl oxide ion and a carboxylate ion. What we find in alkyl oxide ion, that oxygen has a negative charge on it, and secondly, alkyl group exerts a plus I effect, due to which the negative charge is localized over oxygen and it acts as a better nucleophile. Whereas in case of carboxylate ion, the negative charge on oxygen is delocalized over the carboxylate group because of resonance. Hence, it is a weaker nucleophile when compared to alkyl oxide ion. As long as the nucleophilic atom is same, the more basic the nucleophile is, it will be more reactive. Now what you have to remember is, a stronger nucleophile is an ion or a molecule that reacts faster in the SN2 reaction than a weaker nucleophile under same conditions. A strong nucleophile is much more effective than a weak one in attacking electrophilic carbon. Here I would like to take an example of methooxide ion and methanol, which act as nucleophiles when they react with methyl iodide. In this case, we have kept the substrate same and we have changed the nucleophiles. In one case, we are taking methooxide ion as a nucleophile, whereas in the second case, we are taking methanol as a nucleophile. And what was found experimentally? That the reaction with methooxide ion was million times faster, that is 1,000,000 times faster than the reaction of methanol with methyl iodide. So let us look into the reaction here. That is when methooxide ion, which is a conjugate base of methanol, reacts with methyl iodide, it forms a transition state. And this is where you have to note that in the transition state, the negative charge is shared by the oxygen of the methoxide ion and the iodide ion, which is the leaving group. So the negative charge is delocalized. Hence, this transition state is more stable and it has lower energy of activation and the rate of reaction is high. Whereas, when we talk of a reaction of methanol with methyl iodide, here we find that in transition state, it is only the iodide, which is the leaving group, has a negative charge on it, whereas oxygen has a positive charge on it. Now, since there is charge separation in this transition state, it is less stable as compared to the transition state which we had obtained by the reaction of methooxide ion with methyl iodide. Hence, the energy of activation here will be high and the rate of reaction will be low. So we can conclude from here that the conjugate base of an acid is a stronger nucleophile. Now, if we consider periodic table, then what we find that as we go from left to right in the periodic table, here again nucleophilicity parallels basicity. That is, nucleophilicity as well as basicity decreases as we go from left to right in the periodic table. This is because the electronegativity increases from left to right in periodic table. And we know that more electronegative elements have more tightly held non-bonding electrons that are less reactive towards forming new bonds. Hence, what we find is that methanite ion is more nucleophilic as compared to ammonia, which is more nucleophilic as compared to OH hydroxyl group, whereas fluoride is least nucleophilic. So in this case, what we've compared the electronegativities of carbon in case of methanite, nitrogen in case of ammonia, amino group, OH in oxygen in case of hydroxyl group, and fluorine in case of fluoride and ion. Now, however, when we go down the group, nucleophilicity gets inversely related to basicity. Nucleophilicity increases down the periodic table as the size and the polarizability of atoms increase, while the electronegativity of the atom decreases. As a result of which, if we look into the halogen family, then what we find is that iodide is the best nucleophile, followed by bromide, chloride, and fluoride is least nucleophilic in nature. This is because as one goes down the column in the periodic table, the atoms become larger with more electrons at a greater distance from the nucleus. The new electrons are more loosely held and the atom is more polarizable. As electrons can move more freely towards a positive charge, This will result in a stronger bond formation in the transition state. The increased mobility of its electrons enhances the atom's ability to begin to form a bond at a relatively long distance. For example, the outer shell of iodide ion is the fifth shell. These electrons are loosely held, making iodide a soft nucleophile. That is, it is highly polarizable. So since it is highly polarizable, the outer electrons begin to shift and overlap with the back lobe of sp3 hybridized carbon atom from a large distance. There is a great deal of bonding between iodide and carbon in the transition state, which lowers the energy of transition state. This is what I've shown on your slides, that iodide being a larger atom and more polarizable, its electrons are loosely bound and it starts making a bond with the back lobe of sp3 hybridized orbital of carbon from a longer distance, as a result of which there is more bonding between the nucleophile and the electrophilic carbon and in the transition state. This stabilizes the transition state and the energy of activation is less and the reaction occurs better. Whereas if we talk of an outer shell of the fluoride ion, then it is the second shell. These electrons are tightly held to the nucleus. Fluoride is a hard nucleophile, that is, it is not polarizable, and its nucleus must approach the carbon nucleus quite closely before the electrons can begin to overlap and form a bond. In the transition state, there is little bonding between fluorine and carbon. This is what again I have shown here, that since fluoride has tightly bound electrons, it will form a bond with carbon when it is very close to carbon. And in the transition state, there is little bonding between the fluoride ion and the back lobe of sp3 hybridized carbon, as a result of which this transition state is not stable and the rate of the reaction will be low. So we can say among related atoms, polarizability increases with increasing size. Thus, iodide is the most polarizable and most nucleophilic halide ion and fluoride the least. Now let us look as to how does the solvent affect the nucleophilicity. Nucleophilicity is not a property inherent to a given species. It can be affected by the solvent in which the reaction is being carried out. Therefore, before discussing the effect of solvents on nucleophilicity, let us know the different type of solvents. Solvents can be broadly classified into polar and non-polar. And then polar solvents can be further subdivided into protic solvents and aprotic solvents. So what do we mean by a non-polar solvent? A non-polar solvent is the one in which there are bonds between atoms with similar electronegativities, such as carbon and hydrogen, and for an example we can consider hexane. Non-polar solvents are not capable of strong hydrogen bonds or dipole-dipole or dipole-ion interactions, and since they are non-polar, we cannot carry out nucleophilic substitution reactions here, because in nucleophilic substitution reactions our substrates are polars and maybe they can be ionic also. So the second category of solvents are polar solvents. Polar solvents contain bonds between atoms with different electronegativities, such as oxygen and hydrogen, and they have large dipole moments. These polar solvents are capable of forming hydrogen bonds with water. Polar solvents can be further divided into protic as well as aprotic solvents. Polar protic solvents are capable of hydrogen bonding because they contain at least one hydrogen atom connected to an electronegative atom, such as oxygen may be attached to hydrogen or hydrogen may also be attached to nitrogen. In both these cases, oxygen as well as nitrogen both are more electronegative than hydrogen. And these solvents will solvate cations and anions effectively through hydrogen bonding. So here I have shown an example of few polar protic solvents like tertiary butanol, N-propanol, ethanol, methanol, ammonia, acetic acid, water. All of these are protic solvents. And what I have indicated here, the more electronegative atoms are depicted in red. That means the hydrogen which is attached to oxygen in tertiary butanol is protic, that is, it can be given off as proton. That is, this molecule is acidic in nature. Now you have to be very careful here. The hydrogens which are attached to carbon in tertiary butanol are not acidic in nature, since there is very little difference in electronegativity of the carbon and the hydrogen. Similarly, in all other examples, what we find that the hydrogens which are attached to atoms which are depicted in red are protic or are acidic in nature, and they are capable of forming hydrogen bonds. Now, if we talk of a polar aprotic solvent, then polar aprotic solvent contains no hydrogen bonds connected directly to an electronegative atom and are not capable of hydrogen bonding. For example, acetone, N,N-dimethylformamide, acetonitrile and dimethyl sulfur oxide are all examples of polar aprotic solvents. If we look into example of acetone, then in acetone, carbonyl group is polar in nature, since carbon has a partial positive charge and oxygen has a partial negative charge. Since oxygen is more electronegative as compared to carbon, it will pull electrons towards itself. So they are polar solvents. They are not aprotic because a hydrogen atom is not attached to the electronegative atoms in these compounds. Another factor which will affect the nucleophilicity of ions is their solvation, particularly in protic solvents, because we know protic solvents are capable of forming hydrogen bonds, so they will solvate a nucleophile or an electrophile. A polar protic solvent can participate, as I've already said, in hydrogen bonding with a nucleophile, creating a shell of solvent molecules around it, hence stabilizing it and decreasing its nucleophilicity. The nucleophile is considerably less reactive, as so wherever it goes, its lone pair of electrons are interacting with the electron-poor hydrogen atoms of the solvent. We can imagine this phenomena if we compare it. Let us imagine that a nucleophile is a celebrity which is mobbed by a crowd wherever it goes. So in this case, let us compare or equate nucleophile to a celebrity, and the crowd to electron deficient hydrogen atoms. So wherever the nucleophile is going, its way is being stopped by electron deficient hydrogen atoms. Hence, it fails to occur as a nucleophile, or it will have to use some energy to disperse that crowd, and then only it can act as a nucleophile. Here I have shown that a chloride anion is stabilized by hydrogen bonding by the water molecule. So in this what we see is that the chloride ion is being stabilized by the positive charge on hydrogen because of the presence of the OH, because it is attached to oxygen in water, and oxygen being slightly more electronegative than hydrogen pulls the electron towards itself, as a result of which a dipole is created in the molecule, and the water molecules align itself in such a manner that hydrogen, which is slightly positively charged, is encasing the negatively charged chloride. As a result of ion dipole attractive forces, this chloride ion is being solvated with the water molecule, and it fails to act as a good nucleophile in protic polar solvents. The second thing that you have to keep in mind is that small anions like fluoride are solvated more strongly than large anions like iodide in a protic solvent, because the solvent approaches a small anion more closely and forms stronger hydrogen bonds. As you can see on your slides, here the fluoride anion is solvated more strongly by alcohol, which we are using here as a solvent, as compared to iodide ion, whose size is large. Therefore, fluoride anion is a weaker nucleophile as compared to iodide ion, because when an anion reacts as a nucleophile, energy is required to strip off some of solvent molecules, breaking some of the hydrogen bonds that stabilize the solvated anion. More energy is required to strip off solvent from a small, strongly solvated ion such as fluoride than from a large, diffused, less strongly solvated ion like iodide. The enhanced solvation of smaller nucleophile in protic solvents requires more energy to strip off their solvent molecules, reducing their nucleophilicity. Therefore, nucleophilicity in protic solvent generally increases down a column in the periodic table. That is, iodide is the strongest nucleophile, whereas fluoride is the weakest nucleophile in protic solvents. Now, if we talk of polar aprotic solvents, then we know that polar aprotic solvents have strong dipole moment to enhance solubility. Yet they have no groups to form hydrogen bonds with nucleophiles. Like acetonitrile is a protic solvent because of the difference in electronegativity of carbon and the nitrogen attached to it in the nitrile group. Whereas in dimethyl formamide, the formyl group is polar because of difference in electronegativity of carbon and oxygen attached to it. And as I have already said, that acetone is polar in nature because of the presence of polar carbonyl group. Here the difference in polarity is because of the difference in electronegativity of the carbon and the more electronegative oxygen attached to it. A polar aprotic solvent does not hydrogen bond to nucleophile meaning that nucleophile can easily access the electrophilic carbon atom. Under these conditions, nucleophilicity correlates well with basicity, and fluoride ion, being the most unstable and most basic halide ion, reacts fastest with electrophiles. Polar aprotic solvents therefore work very well for SN2 reactions because they do not solvate nucleophiles, and fluoride anion is the most nucleophilic ion, followed by chloride, bromide and iodide in aprotic polar solvents. Now for an example, if we want to carry out a reaction of an alkyl halide with fluoride in methanol, we cannot bring about this reaction because the nucleophilicity of the fluoride ion is reduced in protic polar solvents. Whereas if we carry out this reaction in presence of a crown ether as a solvent, this ether will solvate potassium and not fluoride ions, as shown on your slides. Now what do we mean by saying it's crown ether? Crown ether is a cyclic ether and it has 18, means it has 18 atoms, out of which 6 atoms are oxygen atoms, and these oxygen atoms have negative charge on it. So they are negative because of the presence of lone pair of electrons on it. They will solvate the cation here and not the anion, and the fluoride anion is now naked and it will act as a strong nucleophile. Here I have shown the reaction of benzyl chloride with potassium fluoride in presence of 18 crown 6, that is crown ether, in presence of acetonitrile, when benzyl chloride is converted to benzyl fluoride, because here potassium, the crown ether is solvating the potassium cation, that is potassium, leaving behind naked fluoride anion, which then acts as a strong nucleophile. Another thing that we have to take into consideration is that even if the nucleophilic atom is the same, but if that particular species is bulky in nature, then in that case nucleophilicity will not parallel basicity. Because as I said in the beginning of the lecture, a base is a species which will react with a proton, and when it is reacting with proton, it is reacting with s orbital. Whereas when we talk of a nucleophile, then in that case nucleophile is reacting with the back lobe of an sp3 hybridized carbon, which is little difficult. So in this case the nucleophilicity will be reverse of basicity. So as I've already said, to serve as a nucleophile, an ion or a molecule must get close to carbon atom to attack it. Bulky groups of the nucleophile hinder this approach, as orbitals at carbon that participate in reactions are less accessible than protons, and the reaction rate is slow. So if we compare the nucleophilicity and basicity of tertiary butyl oxide with etho oxide, it is clear that tertiary butyl oxide is a stronger base, but nevertheless it is a poor nucleophile. Tertiary butoxide has 3 methyl groups that hinder any close approach to a electrophilic carbon atom. Here I have shown again the structures of tertiary butoxide, and here what we find is that the carbon is attached to 3 methyl groups. So there is steric hindrance in this case, it will act as a strong base, because these three methyl groups, because of their plus I effect, will increase the negative charge on oxygen. So this can react easily with a proton. But when the question comes of it approaching a carbon atom, which is sp3 hybridized, then these three bulky methyl groups will offer steric hindrance, and it will not be able to access that carbon. Whereas if we talk of an ethoxide ion, then it is a weaker base as compared to tertiary butoxide ion, yet it is a stronger nucleophile since it can easily form a bond with the carbon atom. So therefore, we can conclude that ethoxide ion is a stronger nucleophile than tertiary butoxide ion, and we say when the bulky groups interfere with the reaction by virtue of their size, we call this effect a steric hindrance. So now the bottom line here is that bulkier a given nucleophile, it will be slower will be the rate of reaction, and therefore lower is its nucleophilicity. So methoxide ion, which is least bulky, is the best nucleophile, followed by an ethoxide ion, then a isopropooxide ion, and worst nucleophile is the tertiary butoxide ion, which is most bulky. Now, on the basis of the discussion of this lecture, we can classify nucleophiles as very good nucleophiles, which are iodide, thiols, good nucleophiles, which are bromides, hydroxy groups, alkoxy groups, cyanides. Fair nucleophiles are ammonia, chloride, fluoride, and the carboxylate group. Weak nucleophiles are water and alcohol, and very weak nucleophiles are carboxylic acids. Hence, on the basis of today's discussion, we can say that if the nucleophilic atom is the same, then the nucleophile, which is a stronger base of a conjugate acid, will be a better nucleophile. As we go across left to right in the periodic table, nucleophilicity as well as basicity will decrease. This is because the electronegativity of the atoms will increase. And if we talk of nucleophilicity down the group, then in protic solvent, the order of nucleophilicity will be fluoride will be least nucleophilic, whereas iodide will be most nucleophilic. And if we talk of aprotic polar solvents, then nucleophilicity parallels basicity, that is fluoride will be most nucleophilic and iodide will be least nucleophilic. And if there are bulky groups present on the nucleophile and the atom responsible for nucleophilicity is the same, then because of the presence of the bulky groups, the bulky base will be a poor nucleophile. At the same time, it will be a good base because then it will be abstracting a proton, whereas when it acts as a nucleophile, it will have to approach carbon atom, which will be little difficult. Thank you.